really need to say something to test this out.
Oh, no, the other way around.
Hello, can you hear me?
Yes, we can hear you. Hi, Jim.
Hi, Melissa. I just wanted to apologize for not being there in person. I'm hoping to be back this evening. Yeah, we had a bit of I'm in Philadelphia for a wedding over the weekend, and we had a bit of a hold up, so traveling back today instead of yesterday.
And he's not feeling well.
Oh,
He will be on the,
okay, great.
yeah, he'll be listening to your talk, but he can't come in person.
I'm excited. I was excited to see the film is being live streamed later this week Wednesday,
Oh.
but or I don't know. It's on my calendar. I'm excited to watch it.
And I'm hearing there is some kind of exciting announcement by the EHT on Thursday.
There is? Which Thursday?
This Thursday.
This Thursday?
Yeah, supposedly. I don't know.
Wow, okay. Problem with this hybrid mode is everybody makes a split decision
Yeah.
at the moment, shall I go to the talk or shall I just watch on the computer? It's not the same, at least in my experience.
Yeah.
Coming for the talk is so much better.
Yeah. This is, I think, my first talk in person.
Wow.
Not only pre-pandemic, but last time I was this pregnant. So I was doing that math on the airport. I was like, I really like,
Wow, okay.
hopefully like the pandemic is a good enough excuse for like that long alone. But I don't know. I think I got back to teaching this semester, and that obviously is a huge difference in person.
Right, yeah. Even if you're saying exactly the same thing, it's just so different.
Yeah.
Still two-dimensional. It's a
Exactly.
projection.
It's
So
two-dimensional.
something is lost.
Right.
But if you're away, it's a lifesaver.
Yeah.
If you can't attend.
Yeah, exactly. It's a boon, right? Like, Jamie was saying, she's away.
Right.
And it's so much better than just missing it altogether.
Yes, I'm sorry I can't be there in person. I'm just waiting. I've been traveling, Peter Gallison here. I've been traveling the last 8-9 days, and I just want to get my PCR test back before I come in.
Very reasonable.
Except, Peter, we no longer have to test.
I know. I'm ignoring that change. I'm continuing to test every week.
Oh, is that what you advise for all of us?
Look, I went into physics precisely to avoid thinking about the interior of the body. So what do I know? But a lot of people depend on me, so I need to not give them COVID. I've got 91-year-old parents and various grandchildren, and I just need to, be careful.
Yeah.
Okay, I think we're ready to start. All right, so hello everybody here in the Zoom. So today we're very happy to have Melissa Jacquart with us. So Melissa is a faculty at the University of Cincinnati, the Philosophy department, where she's also Associate Director for the Center for Public Engagement with Science. Her research is on epistemological issues in the philosophy of science. And today she's going to tell us about dark matter, computer simulations, and the philosophy of astrophysics. Take it away.
Great, thank you. And thank you all for having me. So before I start my talk, since I know this can be a mixed audience sometimes, I want to just briefly tell you about some of my orienting research interests as a philosopher of astrophysics. So essentially, my research attempts to understand and assess the use of models and computer simulations in science and their role in astrophysics and astrophysical methodology. Namely, I think there's something really interesting about challenges that astrophysics in particular faces in being able to generate reliable inferences from the use of models and computer simulations. So I'm interested in understanding how scientists construct models and computer simulations, assessing what it means when a scientist says they have a successful model or computer simulation, and how such claims are evaluated by the scientific community more generally. So I'm interested in how astrophysics can generate also reliable inferences about the objects of their study. And so that is really going to be the overall focus of my talk today. I'm going to start out by sketching some interesting methodological issues and challenges that are faced by astrophysicists, specifically connected to the use of models and computer simulations. And then the rest of my talk is going to focus on discussing how astrophysicists go about addressing these challenges. And to facilitate this, I'm going to do what's very common in philosophy is I'm going to pick a case study related to some work that I'm currently doing connected to dark matter and ring galaxies. So I'll take a brief interlude to talk a bit about some science, and then I'll provide some philosophical analysis related to what grounds the viability of simulations in my research project and how they're used to characterize the morphology and confirm dynamics of real-world systems. So this is roughly my plan. Okay, so now there are many ways that scientists obviously go about investigating the world. Some sciences conduct experiments, but in some sciences, obviously that's really hard, and in some impossible. And so in these cases is often where we turn to models and computer simulations. But there are also challenges that astrophysicists face by trying to understand how to generate knowledge from those models and computer simulations. Models and computer simulations, by their very nature, are not going to be perfect replications of the real world or the real systems. They're necessarily incomplete representations. They're partial descriptions and don't have all the features of the actual world. And so in the process of building models in computer simulations, various idealizations are made by the simulationists, as well as various approximations, obviously. And so here is just a whole host of these kind of examples. In building these kinds of models and computer simulations of structure for the universe, for example, some features of the target system necessarily must be left out. And there's sort of varying extremes to how many features are left out and how many are included. For example, those here in the left column only include dark matter and exclude baryonic matter, and that's thought to be a reasonable assumption to make. And obviously none of these include every aspect or every galaxy in the system, again, something that the scientific community or some of the simulationists judge as a reasonable claim to make. And in all of these cases, again, this idea of idealizations and approximations are being made by the simulators. But despite these simulations not having all the features, astrophysicists think that the models can help us generate reliable knowledge about the real world systems. Okay. So on some cases, it's evaluated that these simulations are quite good. We're quite pleased with these simulations. This is one that I think is often used as an exemplar of a good simulation, getting the large scale structure quite right when being compared to observations. So here SDSS observations compared with the Millennium simulations. And this is one that's often assessed as being quite good. Now, here's another example where one might not be assessed as being quite successful. So on the left here is an example of computer simulations and what they predict our local area of the universe to look like. And so again, wherever you see a dot, that's where a galaxy with dark matter should be. On the right, however, are all the galaxies we actually see. And as you can see, there's quite a lot less. And so this is often one considered to bring about a real problem. You know, astrophysicists are only able to account for a fraction of the dark matter that's supposed to exist in the universe. And so one of the big questions ends up being, where is the simulation's predicted dark matter? Where are the missing satellites? And so these kinds of questions related to simulations have emerged because of some tensions related to simulations and observations. And so what I want to do is highlight briefly why, as a philosopher, I think getting a better understanding of the relationship between observations and simulations is so important in this context. And it's due to one of the methodological challenges that we're up against in astrophysics. Like I said, by its very nature, astronomers can only can't perform experiments, especially on stars, galaxies, the whole universe in any material way. There isn't anything to interact with directly. Astrophysicists, for example, can't take two galaxies and smash them together in real life and see how they evolve over time. You can only observe either what's already happened or piece things together. And so this is to say that it faces an observation-based epistemic challenge. In some sense, the subjects themselves cannot be manipulated experimentally. There's also, I think, a really interesting issue in astronomy related to sparseness of data. So that is, we only have often one snapshot of objects under investigation. And while we can obtain data, say, along various electromagnetic spectrums, so you can get the optical, radio, X-ray, you don't have access to watching these things evolve over time the way a lot of other sciences do. And so how astrophysicists have been getting around this, obviously, is by bringing in computer simulations to allow one to try and better understand these systems in a case where there is little to no direct access or incorporation of what one does have direct access to ends up becoming really critical. And so too then is understanding how observations and computer simulations work together as evidence for these kinds of claims. So within astronomy, this is all relatively common, this is straightforward, but within the context of the philosophy of science literature, there has been an extensive debate about the epistemic status of computer simulations. So some philosophers have argued what's called a materiality thesis, in which the material object target correspondence ends up being this defining feature for experiments, but not for computer simulations. And what some philosophers argue is that this ends up giving experimenters a real advantage. The suspicion or conviction by some of these philosophers is that an experimenter simply has more direct epistemic access to the target system than the simulationist does. And as such, computer simulations necessarily will always be inferior to real experiments. So on the other side of things, there are also some philosophers that argue that this material correspondence is not, nor should not be thought of as necessarily the best route to valid scientific inferences. And so in connecting this to the case of astrophysics, there is, again, in some cases, no physical way to interact with manipulate these kinds of physical systems being investigated the way a traditional experiment might be. So the simulationists this is their only means to interact with it. And so it seems that we don't want to have to say that these kinds of sciences will always be epistemically inferior to those of the experimentalists. All right, yeah.
Question. You're framing this, and I missed the first part of the talk, so forgive me, as though experiment and simulation are in tension.
Yeah.
That they're almost oppositional.
Yeah.
Whereas I tend to think of simulations as guiding. experimentation.
Yeah.
You know, if you didn't have some of the simulations, you wouldn't quite know what kind of instrumentation to build to carry out an experiment or to make an observation.
Yeah.
So aren't they somehow two sides of the same coin?
Yeah, I think that's right. And so that's actually sort of the starting point that I want to start a lot of my work from.
So let me-
Excellent.
I will just be quiet.
No. I always say a good philosophy talk to physicists is set up well where my next point answers your next question. So given that there are these challenges, part of how I approach my research that is a bit different from how other philosophers may have in the past is I don't want to view this as sort of like a false dichotomy, as it's either experiments are the best and most authentic or the most rigorous way to go, or that computer simulations have to live up to the standards that are set out by experiments. I think that this is a false dichotomy, and rather than showing how they don't meet these standards that philosophers have prescribed, I'm interested in trying to determine, or if computer simulations need to be classified in the same ways as the experiments, I'm interested in looking at how in practice these things are used together. And so my choice of starting position is how to try and figure out how the practice of computer simulations and observations together lead to them obtaining certain epistemic statuses within the field, and how that interwoven relationship can go about in being characterized and ultimately enhance the kinds of arguments that scientists might want to make, especially when computer simulations are central to the scientific argumentations being made. So that is to say, I think there needs to be a deeper and richer exploration and understanding of the relationship between observations, experimentation, and simulation. Okay. So again, just sort of getting some of the research questions that I'm interested in and will be the focal point in this talk. When a philosopher of science who analyzes computer simulations and astrophysics, I think there are a few important questions that need to be attended to. So the fact is that for a lot of astrophysicists, reasoning for claims is tied to this relationship between observation, theory, and computer simulations. So as I said, I'm trying to understand what this relationship is. I also want to see what we can learn from looking at computer simulations in this context, as a significant amount of the reasoning is tied to that. So two other questions I'm really interested in are under what conditions indirect observation of modeling and computer simulation is convincing as direct observation, what grounds the viability of simulations to characterize for morphology and confirm dynamics in a real world system, and how astrophysicists ground the inferential power of computer simulations. What sort of approximations, idealizations are made, how are they handled or mediated, and how are the simulations then used to enhance the observational piece or to lead to future explorations. So these are the kinds of questions I'm interested in. So now let me tell you a little bit more about how I'm going about to answer some of these. So I consider myself to be doing what's called within the philosophy community embedded philosophy of science. Much like some of your philosophers that are here, I'm doing both the science and the philosophy. And I'm working closely with members of the scientific community that is the subject of my philosophical work. And as such, my research team is really interdisciplinary. And so we are made up of astrophysicists, philosophers, as well as citizen scientists. And so we're currently working on a project related to dark matter and ring galaxies. And so we're doing some of the science and then alongside doing some of the philosophical analysis of this scientific work. And so that's what I'm going to talk a little bit more about today is the science case study that I happen to work on, which uses observation simulations. And so I'll talk a little bit about that science and then zoom back out to some of the philosophy. Okay, So recall, one of the things I just mentioned is this outstanding problem in modern astrophysics, that there is this mismatch between dark matter mass accounted for observationally based on the luminous galaxies we see, and the amount of dark matter that is predicted to exist by cosmological simulations. And the question being, where is this missing dark matter? So the group that I am running is exploring a possible answer to this question. So one of the critical assumptions in the missing satellites problem is the coupling of dark matter to baryonic matter. And so our working hypothesis for our group is what we're calling a dark galaxy hypothesis. Well, the missing satellites and too big to fail problem suggests that dark matter halos always have a luminous component. We're exploring the possibility that this might not be the case. That there is at least some of this missing dark matter in what we're calling dark galaxies. That is pure dark matter halos that have no visible baryonic matter, either because they lost that mass very early on, or they never acquired it in the first place. So of course, there's this question of how could dark galaxy actually be found, given the assumption is that dark matter is not directly observable. We only observe it through gravitational interactions with baryonic matter. So our proposal is that some of the missing dark matter galaxies can still be found by these effects, and we're going to use dark matter's ability to interact with visible galaxies as using gravity as either a marker or a signature for its presence. So as I mentioned, again, part of astrophysics is in some sense confined to snapshot observations. Here are some of our most standard snapshots. What most galaxies look like, spiral or elliptical. So here are some more snapshots. And these galaxy structures are called ring galaxies. Now, it turns out that galaxies of this shape are rather rare in the universe. This shape does not occur naturally the way spiral or elliptical galaxies do. These are collisional ring galaxies, and they get their ring shape only when a galaxy of just the right size undergoes a near head-on collision with another galaxy of just the right size. So these are some of my favorites. It's obviously a ring. This one is really fun because you can actually see the companion galaxy smashing through it in the upper corner. And then this is one of the most standard ones folks have seen, the Cartwheel Galaxy. So astronomers have known about ring galaxies for some time, as far back as 1976. They were able to use computer simulations as a tool in attempting to understand how these rings got their shape. And so in these early simulations, there wasn't any need to capture the exact trajectory of every particle. They simply wanted to provide these kinds of how possibly accounts for how these rings might have gotten their shape. So the masses of the two galaxies were varied as a means for exploring how they might interact, as well as conditions that are necessary for these ring galaxies to obtain their shape. And these are some of the earliest simulations proceeding over time to develop the ring galaxy as the companion. The little dot collides with it. And so here you're seeing the ring shape. Here's often what the whole galaxy will sort of bend if you see it on an edge-on sense. And that's roughly what they look like. And so here's going to be another simulation of these ring galaxy collisions. So this is going to be a collision between an elliptical and a spiral galaxy to form a ring galaxy. Now the left image up there is a snapshot. It's its actual observation that this simulation is based on. And then on the right is going to be the point particle simulation. And so what you're going to see is essentially how these galaxies get formed. So right now the other galaxy is way off screen, and it's going to come up, collide, form essentially identical ring galaxy formation to the snapshot. And then after a few rotations, the rings often dissipate, and then the two galaxies end up merging together. Okay. So here are two more actual ring galaxies, and these two happen to be almost identical in structure. So most of these ring galaxies have a clear companion, another galaxy that collided with it and as a result created this ring. On the right here is ARC 147 and its companion. However, in looking through a catalog of peculiar galaxies, there have been a handful of ring galaxies that have no clear companion, and these only form by undergoing a collision. So on the left is Zwicky 28, and it's a ring galaxy that has no visible companion. You might think it's some of the objects in the background or that it's embedded in the ring, but the other objects are too far behind it.
Sorry.
Yeah.
What's the time scale of the dissipation of the ring?
Ooh.
As I can imagine that as a, it's just like a spherically actually pulling out all the matters, and you see it actually in a projection like a ring, right?
Yeah.
But as it goes, it might, like what you say, it would actually get distracted and just say, just goes away or just get accreted to the central.
Yeah. So I don't remember it. I mean, it's on the orders of a few million years. And so I have a simulation later that I think has a time scale for how long they take to dissipate. I didn't make that one, so I don't have the time scale on the one that I just showed. But they do take a while to go away. And one of the other things that we're still sort of trying to figure out in learning about ring galaxies is what the average age of them are. And so part of how we're doing that is lining up these snapshots of what we think are its various stages in progression and trying to get a sense from that as well.
And a follow-up is that, is there any inclination limit of the second progenitor that comes through? Because if it goes like on the up versus on the edge, again on the edge would be the best way to actually to put it. But if this is another angle incline, I don't think that would be super symmetric ring, right?
Yeah, that's right. And so in fact, to get the ring shape, it has to be virtually near head on with it.
Okay.
Anything else, it doesn't make that same ring shape. Yeah, so that's, yeah.
I was just kind of surprised that the colliding galaxy seems to always maintain its structure as it's going through the ring. Does that always happen, or will they sometimes get obliterated as they go through the ring?
So there's almost always, and this is another thing we're exploring in some of the computer simulations I'll show you in a bit, but there is a sense in which some part of it always does pass through to some extent. And so there have been very few cases that we've been able to develop, again, within our computer simulations, where we've been able to have the other mass totally dissipate. Again, it's a trade-off between how much mass you need so that you actually see the ring structure as a result of the collision, versus if it's not massive enough, that's when it might not come out the other end. But then it's also a case where we often don't see the ring galaxy structure. Yeah, these things are really fascinating in terms of just how particular I say settings because I do this in computer simulations, but just how particular the conditions for them to occur are. So it's super interesting. All right, so with Zwicky 28, we have no collider or visible collider anyway. And so again, you might think that it's been sort of like dissipated or that it sort of got sucked up in some ways in there. But again, a lot of the simulations don't seem to support that. And so the hypothesis that we're exploring is that this still had a collider. It's just it was a pure dark matter halo collider. And so and that's obviously why we can't necessarily see it there, because it's pure dark matter. So our goal is that through these simulations, we're trying to figure out the various ring structures that can happen and figure out under what conditions this might happen in certain cases and how that would look like if it is a pure dark matter halo collider.
So before you change the slide, the ARC 147, is that really two rings?
Yeah, so that'll happen sometimes. And I can't remember exactly, but we have a couple cases where we've ended up seeing almost like a double ring feature. Yeah.
So in this case, would you say that the bullet that went through is the guy on the left?
Yeah.
Okay.
Or it might also, no, that wouldn't be right because of the color, but yeah.
Okay.
Okay, so we're trying to figure out these simulations. How do we build this up from there? So obviously, one of the best places to start is learning from the cases where you can see both of the galaxies. So we've been looking at a host of luminous-luminous interactions. And so we've looked through catalogs of ring collisions, and part of what we've done is then taken these observations of these systems where we can see both of them and build simulations for what those collisions might look like. So this is just one example. The left is our optical image. The middle is spectroscopic data, which gives us a velocity field. And this information ends up becoming the basis for our simulations. And then the image on the right is our simulation of the actual data. Informed and constructed with the data that we actually know about the observation, namely its general composition and its mass. Okay, and so from looking at luminous galaxy collisions, there's this host of key defining properties that all collisional ring galaxies share. So namely, they all have a narrow globally defined ring. Because of the collision, they always have this blue young stellar population. They're always rotating in a very particular way. They're always expanding in a very particular way. Their companion, when you're trying to figure out who might be the collider, is almost always along the minor axis. And there's always this off-center nucleus. And so these end up being what guides the building and evaluation then of our dark matter luminous galaxy collisions, and also our search for some more potential isolated ring galaxies. So these ones where we don't see the clear companion. So thus far, our collisional ring galaxy candidates have come from extensive catalogs that have been published. Most notably the Atlas of Peculiar Galaxies by Arp and Medor. ChooseWiki 28 is our most promising isolated ring galaxy from those, but we're also trying to find more. One of the strategies we've used is trying to see if we can work with NASA's Galaxy Zoo to find more of these, but unfortunately, when it comes to ring galaxy, the citizen scientists who are classifying these aren't doing a super job at it. However, we have developed a partnership with one of these citizen scientists that's very devoted to looking through galaxies. And he's found hundreds of additional ring galaxies through some new field surveys. So, and some of these also appear to be isolated, and we've also even found a double ring, which is really exciting. Okay, so we're trying to find these based on snapshots and see a host of variety of these. We're also in the process of building a catalog of spectroscopic observations and getting data cubes of these potentially isolated rings. This is really helpful because not only it lets us learn about what's in the galaxy based on absorption and emission lines, but it also allows us to obtain the velocity fields. So that's the observational side of things. In parallel to this, we're working on building simulations, as I mentioned, and especially of ChooseWiki 28 and of dark luminous galaxy collisions in general. Yeah.
I'm just curious, what's that vertical line for?
So this is us taking observations at the Magellan telescopes. And part of what we have to do in order to build up the data cube is essentially move this slit painstakingly across this, at least using that telescope. So that's the best way to get the data cubes. So the slit is what's being observed. And so essentially you just move that across. It builds out your data cube, and then that is what then gives us our velocity
So
field.
that's why those vertical lines not plotted.
Yeah, yeah, roughly those are the data at that point.
Sorry, I wanted to know, is there any constraints on the location where these dark matters come from, or to build up the ring? Does that have anything to do with the impact parameter of the second galaxy that is, colliding with the first one, or?
So for the ones that we're building, we're basically going to assume sort of like standard composition of dark matter profiles and where they might be in the galaxies. Yeah.
I'm just saying radially. Do you know where they are coming from? The rings, because this ring is coming from maybe the first progenitor, right?
Yeah,
And how do we know where they are coming from?
yeah, that I'm not entirely sure.
Okay.
But
because from the simulation perspective, it's just very easy to follow them, right? As a second basically snapshot, all what you need to do is just like to track their ID numbers and just bring it back to where they are.
Yeah.
And that would actually bring me to the second question, that why not the star? Because the star always follow dark matter. So is this going to be on the outskirts of the galaxy when you don't have enough star or something like that?
Yeah, so I think the simulations and some of the data that I have in the next couple slides might answer that question.
Okay.
But again, ultimately, because of sort of like the mass trade-off, we don't think stars are like the best likely candidate for this kind of thing either. But let me see if my next set answers your question, and if not, ask me again.
All right.
Okay, cool. Okay, so this is what we're doing on sort of the simulation side of things. So we're using the Gizmo simulation codes. And so we're using these primarily because they house a lot of the background theory and knowledge, namely components of the universe. So part of what we're doing is taking a lambda-equal dark matter understanding of the universe. This also allows for some flexibility in terms of inputs of initial conditions. So namely, we're taking ours to be the CMB. This helps us constrain sort of that possibility space of configurations that the particles can take in the simulations. And then obviously the laws of physics, and it being that gravity is what's driving a lot of the structure formations in these cases. One of the really interesting things in contrast to previous simulation codes, like the point particle ones that I was just showing you, Gizmo is one of the first codes to really prioritize the inclusion of fluid dynamics and star formation and feedback as a critical part to building the simulations. So prior simulations have typically left out these features. And we're trying to find ways to include them because though it might not be as relevant on large scales and large scale structure formation, for how single galaxies develop and evolve, that stuff is really important in terms of how the systems evolve over time. And I'll just make a small plug here. If anybody here happens to work with Gizmo or FIRE as simulations, I would love to talk to you more about them. But one of the things that we're trying to do is include this feedback because it'll help hopefully increase the predictive power of the galaxy formation simulations without doing a lot of fine tuning of the galaxy formation models. And from a philosopher's perspective, I think this is rather critical for the case of simulating individual galaxies. And it's also noted by those who have developed sort of the FIRE code. In one of their talks, they've mentioned something to the effect of you shouldn't trust models that don't do stars and ISM right as sort of their slogan, because they're such critical drivers of single galaxy formation. So when you're trying to simulate something like the Milky Way or a single galaxy, they're really important and relevant to getting characteristics right. Okay, so the task to developing the simulations then and trying to do these individual is to build a galaxy that'll undergo this collision. And so in constructing this galaxy, there are a number of parameters that need to be set in the simulations. All of these inputs are based on observational data we have of real luminous galaxies. So these are all of the observation-based inputs. So we're using stellar mass size relations from them, bulge to disk ratios for the target galaxy, gas fractions and mass. Gas scale length is assumed to be 3 times that of the scalar disk scale length. We're using the NFW dark matter halo profile so that the rotation curves lie on the baryonic Tully-Fisher relation. So again, this dealing with some of where the dark matter is already distributed in the luminous galaxy portions. And then we're also drawing on the luminous understandings for total mass to light ratio varying with mass. Okay, so then we get to go to the fun stuff, which is actually trying to hit the galaxy that we've created with a dark matter collider. And so this is what that simulation is going to be. So this will give you a bit of the size. This will give you sort of the time duration of how long it's taking. So I'll start this. So first we start with this stable spiral galaxy. And this is just before the collision with the dark halo. This is gas, this is stars. And we see the ring forming. We see an expanding ring both in the gas and in the stars. And this being sort of the nucleus that I mentioned earlier. And then this is where it ends up. So here it is from some other angles at the start with the actually evolved disk, and then just after the collision, again on the side and from head on or face on. And so these are all the ways in which we are changing the parameters in our simulation and exploring what impacts these end up having on the actual collisions. So we've varied some of the mass ranges, we've changed concentration class, we've changed the shape, various impact parameters, again, sort of what angle it's coming in, the mass range that these have, the gas fraction, and the initial bulge and disk parameters as well.
So the particular experiment you showed,
Yeah.
that had no gas?
So it had some gas.
We didn't see any light.
Let's see. So this is modeling what's going on in the gas.
Yeah,
And this is what's in the stars.
right. But where is the gas in the colliding?
None. So it's pure, the
Okay.
collision is pure dark matter.
But that's not true for all of your experiments, is it?
No. So again, we part of what we've tried to do is learn from the luminous,
Yeah.
and then import what we know about those into this case. But again, part of what we're changing is we're building the sort of standard luminous galaxy that's following a lot of the observation-based understanding. But for the collider, we're doing that with just pure dark matter.
Okay.
Yeah.
Okay.
So do you know where the companion collider went? Because I think you, in the observations, you said it always lied on the y-axis.
Yeah.
Okay.
Yes. Yeah. So here's just another example of different influences the simulation parameters can have. So here is just one of these from this massive list. This is concentration class. Again, one of the interesting things we can learn from the simulations is the higher the concentration class, the more pronounced the ring feature. So again, you might not see the full ring feature if the concentration class isn't as high. So again, here you get a very strong ring, but in these it's much subtler. The other thing that we can get from them is the velocity field, which is really helpful with some of the simulations, because again, this can tell us not only how the ring is behaving, but again, if we're trying to figure out if there are hidden companions behind, they will come up having a different kind of velocity field. And so with a lot of these simulations, the next thing we do is we go back and compare it to the actual objects. So here is our simulation. I've added in basically that red dot is representative of the dark matter and where it is. And this is sort of where that picture looks like. Oops. And then we can go back and compare that both with the actual data that we've taken of the galaxy with respect to its velocity field, the actual optics of the image, and then comparing that with our computer simulation to approximately guess where in the image, if there is a dark matter companion, it should be.
So can I ask another question that's related to what actually she asked? So if you have a spiral galaxy and you have a disk like that, of course, if you go up that way, right, the dark matter just distribute in this plane. But what about if you have an elliptical galaxy? Because elliptical galaxy could be completely spherical, and there is not any like a minor versus the actually major axis, right? Minor perpendicular to the major, to the disk of the galaxy. Yeah. So on that part, do you have any anticipation? How does that look like?
It looks like you don't, with elliptical, when the colliders are like elliptical, you tend to not see any ring formed.
Okay.
Yeah.
I see. Because there's not any preferred direction for the ring to go.
Yeah, and it doesn't have sort of the same sort of like star distribution to see what's actually going on, at least not in what we've been able to figure out based on the array of ring galaxy observations we found and in the simulations. All right, so that's what's going on the simulation side of things. Now, I want to return to the philosophical questions I raised, but I think before I do that, I'm going to speak to another possibility that this group might be interested in is why dark matter colliders and not black hole colliders. Was that your question?
No, sorry,
Okay.
I should ask earlier. I was just curious, like, where the dark matter fit would be in this image. Like, where would that halo be?
Yeah, so where the red dot is, so in the actual observation, I think I cropped this too much, but I can go back. About right there, or here, I can't remember exactly, but yeah. But we don't see anything.
I see. I don't know if it would be possible to see like if you made a guess that it was there, but you actually see like I don't know if there's anything behind it that you if you went to a different wavelength and you could see lensing.
That would be the dream. Yeah. There's a sense in which we have to make this like a plausible case to even get observation time to look at something like that. But yeah, I mean, the dream in looking for these ring galaxies would be to find an isolated ring and to find something lensing it. That would be amazing on so many levels. We have not been that lucky so far, but yeah.
In the chat, Peter Gallison is asking, are the collisions agnostic as to the nature of the dark matter collider? The sense of being baryonic, non-baryonic, HM, etc.
So right now we're sort of just assuming standard dark matter, but one of the things that we like about the computer simulations that we've chose is it's going to give us the possibility to explore different dark matter profiles, like self-interacting dark matter or things like that. All right. So as I said, often when I talk about this in the context of people who know something about black holes, like you all, this is often a question I end up getting, which is why pure dark matter halos? Why not black hole as the plausible cause for the isolated rings? And I think there are two things that I think are helpful to address here. The first is we are ostensibly doing this first kind of testing for pure dark matter halo collisions, which involves looking at a range of possible dark matter halos that could produce these ring galaxies. And we're doing it in this context of the lambda-cool dark matter LSCDM model because it predicts that maybe these halos could exist, but it doesn't overly constrain their relative numbers, their concentration class, or the baryonic to dark matter ratios. But we could just as easily undertake, say, test 2, just by dropping point masses of various sizes through these baryonic galaxies and seeing that they would indeed make these kinds of ring galaxies. And we could put constraints on their properties, of which black holes only have one, their mass, and putting aside spin because that's irrelevant for the context of these collisions. But furthermore, there is little expectation, at least, trying to work within one set of assumptions in astronomy of these free floating black holes being part of the computer simulations. But if we were to do that, we wouldn't necessarily be testing this bigger theory. We would just be probing what sorts of black holes would do the job if they existed in any future cosmological model that might naturally produce them. So that's where sort of black holes fit into all of this. Okay. So that's the astrophysical case study that I'm working with. What I want to do now is zoom back out to some of the bigger philosophical questions I'm interested in. Namely, what grounds the viability of simulations to characterize morphology and confirm dynamics of the real world system? Or in other words, how is it that we move from claims about these simulations to claims about the actual real world? And how ought we understand the claims about our models or computer simulations being successful in this context? Yeah.
It seems kind of interesting because it seems like you first identify some tension between observation and simulations, really that the simulations produce more galaxies than you actually see.
Yeah.
And you're taking the stance that the simulations, I guess, based off some sort of understanding that we hold fundamental. So you're holding that to still be true. You're not necessarily throwing it away.
Yeah. And I think if we look at some of, again, thinking in the philosophical literature, that's, I think, what folks are trying to point to some extent. So one of the options that philosophers talk about anyway is to think about computer simulations and models as this kind of assessment about assessing the or what's called in philosophy adequacy for purpose hypothesis. This is the idea that model or computer simulation M is adequate for some purpose P. So Wendy Parker is a philosopher who examines and argues successful models if they're being evaluated as adequate or sufficient relative to a given purpose. And her take on this is roughly, in order to argue we have confirmed or disconfirmed an adequacy hypothesis, we need to first determine what we are likely to observe if it's true that a model is adequate for the purposes of interest. And then check how well what is actually observed fits with what we're likely to observe if the model is adequate. If what's actually observed fits well enough, then the observation confirms the hypothesis that the model is adequate for the purposes of interest. Okay, and so this is one of the options, is to consider when scientists are making claims about having a successful model as this being tied to an adequacy hypothesis. It's adequate for whatever its purpose is. Yeah.
Are there any issues with the perspective of confirming hypotheses rather than a focus on falsification?
Yeah, so I think that's one of the biggest problems with respect to this is, again, because models and computer simulations have so much of this like wiggle room, you can always sort of like defer and be like, oh, but if we change these parameters, then it does this other thing. If we change this, it does that. So it's at least trying to identify it as trying to make some kind of claim with that regard. Yeah. Another option that exists within the philosophical literature is thinking about this as a similarity assessment. So this is philosophers like Nancy Cartwright, Ronald Gere, Michael Weisberg. They argue that successful scientific models of systems stand in a relation of similarity to their real world systems. Now, one of the things is, part of what I'm trying to do is think about how both of these options work in the context of the case study that I've just talked about. And so I've talked through and detailed the simulations, and I think it's been about getting to some extent the right features in the simulation. Features that we need like blue stars, rotation, expanding. These are determined to be important key properties of ring galaxies. Yet at the same time, it doesn't seem to just be about getting adequate models. There's this desire, or this desire for adequacy is mediated by assessments and prioritization of the simulation's accuracy or similarity to the target system. So for example, all of the various observational data is the basis for a lot of this. So the models are adequate, but it's because their foundation is to the similarity of the observational data. And so similarity also seems to be a really critical aspect in order to ground these types of claims like a pure dark matter halo actually existing, especially when we don't necessarily have that information. We want to get it as similar as possible to what we can actually see. And so I think there's an extent to which, at least within some of the philosophical literature, this is an underappreciated point. What defines adequacy of simulations is similarity. And Wendy Parker herself even acknowledges this to some extent. She says, an adequate model is one that is sufficient for the purposes of interest, not just by chance or luck, but because it's similar enough to the target system with the relevant respects. Which similarities are relevant and what counts as similar enough is determined by the purposes at hand. And it's this grounding in similarity, I think, is what grounds, if you want to make any sort of like realist claims about these models, it's what allows us to move from them just being computer simulations to making claims that though what we've seen in the computer simulation should actually also hold in the real world as well. Again, we should think that because our simulation predicts the dark matter halo being somewhere, we should think that that's true in the real case as well. So to answer sort of the question of what grounds the viability of simulations to characterize morphology and confirm dynamics of the real world system, and how we move from these claims from the simulation to the real world, it seems to be of two parts necessarily. It's partly a matter of an assessment of its adequacy for purpose. Our simulations are adequate. They tell us this is roughly what a ring looks like for the purposes of reproducing them or predicting the dark matter. But I think in order to move from claims from the model or simulation to making claims that they actually hold in the real world, you need some background commitment to some kind of similarity judgment. And in astrophysics, this comes from the models being constructed with strong similarities in the first place, namely grounded in these observations. And I think that sometimes in philosophy, this point is overlooked or not made explicitly enough that this is how this inferential power comes about. And in our case, I think it would be a mistake to characterize the assessment as simply being a model's adequacy to reproduce these ring galaxies or computer simulation's ability to do these ring galaxies, or just that they're similar enough. I think the two come together and work together, but part of what needs to be better characterized is that trade-off of adequacy with similarity. Again, you can't, because of idealizations and approximations, you can't always include everything, so it has to be adequate enough.
Yeah, I'm listening to all the words here. It all makes sense, but there's one fundamental thing I'm unclear about. Who decides what is adequate or what is similar enough?
Yeah.
There's no overall judge who decides this.
No.
This is something internally in the community.
Yeah.
Is that something philosophers worry about?
That's something I worry about.
You worry about, good, yeah, right.
Yeah. And that's what I'm interested in getting a better understanding of, because I think it's also where pushback will come when a line of astronomical reasoning relies heavily on simulations. Is it being either, just fine tuning or just tweaking things? And I think this is the crux of the problem. There is this sense in which it needs to be adequate enough, either for computational power or because you literally can't get all of these things in. But again, one of the things that I think is interesting in the fire simulations is they're adding back in some of those similarity aspects, which is increasing sort of adequacy judgments. But yeah, they seem to happen in trade-off, and it seems to in some ways be reliant on how the scientists go about making that argument and making that justification, but there doesn't seem to be any magic formula. Yeah, I'm very, very fascinated and worried by this, yes. But also to that point, I think there's one other frequently overlooked aspect to assessing models, which is its reliance on purpose. And I think that's another thing that, again, in the philosophical community is under-discussed and something I'm focusing on. And that's, again, if you think of these claims about a model is adequate for a specific purpose, I think the kinds of assessments that are being made also need to be relativized to a purpose, because extension beyond its original purpose might lead to problems. So again, you might develop a kind of model or computer simulation that does a really good job describing particular data. Again, some of these computer simulations are very focused on accurately re-representing the data so that we can have an understanding. But I think sometimes when we deem a model or computer simulation successful in one domain, such as providing a really good descriptive model or being very predictive, it's tempting to think that that should then equally transfer to other kinds of purposes. But I don't think it's necessarily always the case that a good predictive model will also be a good explanatory model, or that a good explanatory model will always make great predictions. And so I think another place where there are tensions about if models or computer simulations are good or successful might also be tracked back to the purpose that it was either originally created for or that it's being put to in a new context, and not being explicit or careful enough in attending to if that is an appropriate re-extension in those cases.
So this is, I think you touched also there a little bit confused about, so when it comes to building computer simulations, they're usually based off some sort of physical intuition. Yeah. And essentially the computer simulation, all it boils down to is an algorithm. Like a lot of times, maybe you want to ask a question, you have some like theoretical framework for producing answers to that question, and maybe you cannot actually get the answer, but you can define an algorithm that will eventually converge that answer.
Yeah.
And when you go to computer simulation, you're implementing the algorithm. Yeah. But then there's some sort of deviation from the idealized implementation, and like they're somewhat different and the same.
Yeah, no, and I think that's part of the interesting thing, but I think it's also one of these places where there might be problems, especially when computer simulations, I mean, I often use climate example as another one. Some climate models are really good at predicting things, but if you want the simulation to explain like, okay, but why is that the prediction? Some of them are quite bad at being able to tell you for any reason, like I don't know, this is just the code that worked really well. And so I think those are the kinds of places we need to be more careful about acknowledging that it may be extremely predictive and it may be a highly successful predictive model, but that doesn't necessarily translate into explanatory success for exactly those points that you raise.
So in terms of predicting versus explaining, is there a sense in which if you ramp up the similarity, your explanatory power should increase, I suppose?
You would hope.
But your predictive power might go down. Is that correct?
You would, that and in some cases is. And I think that's one of the things that, again, it's this trade-off and tension. It always sort of ends up being the particulars of it. I think there are some other interesting cases in astrophysics that might attend to this that I won't bring up here because that's a whole can of worms. But I think there are these cases where those are our intuitions, and those are often what drives us when we're developing models in computer simulations. But I think sometimes we think that they should both go up together, and that's not always the case. That if we get a better predictive model, it should also be explanatory. If we increase the similarity, obviously it should be better at predictive. If we put more of the things that actually make sense, again, when you start adding in stellar feedback and things like that, we get more accurate, potentially simulations, but there is this sort of sense in which understanding sort of what the trade-off of that upper limited computational power is, et cetera. It's a trade-off. All right, so to just conclude, while observations are these promising candidates to give us clues to the origin, it's the simulations that are really going to help constrain the characteristics of the interaction, physical properties of dark matter halos, and give us the predictions that may be useful for these further observations. In the end, the simulations are gaining some of their epistemic warrant from the assessment and prioritizations of the simulation's accuracy or the similarity to the real optical or spectroscopic data. But at the same time, there's this desire mediated by the assessment of the similarity's adequacy. So again, if we provide too many details, we might fail to build a model that works, but we try to construct the simulations without oversimplifying reality. To maximize that similarity without getting too lost in sorts of complexities. And so this, I think, is what allows astrophysics to make the claims about reality based on models and computer simulations. Yeah.
Oh, sorry. Yeah, I'll take. Yeah. Thanks. That was a good talk. Yeah, I didn't realize it was the last slide.
No, that's all right.
Yeah.
it's all a flowing conversation. I'm good with that.
Out of curiosity, like someone gave you a description of how to like build a model, right? And you went and you actually built the simulation yourself, and they told you what settings to put it on in order to get the desired outcome that you're expecting. Would you expect that? Would you consider that to be an explanation or not?
I mean, I guess it's an explanation of what would be my question. I mean, so is it a matter of what kind of explanation are you looking for? Is it why the simulation behaved a certain way? Is it why the ring forms in the specific way it does? I mean, I think in some ways with ours, what's embedded in the code is a lot of that theory, which I think also plays a prominent role. I've talked a lot about observations in this, but I think theory is another one of these background conditions or background information and knowledge that we think is grounding some of that similarity assessment. And so I think some simulations are developed with attendance and mindfulness to how those things correspond to either the theory or whatnot, but I don't think that that's always the case. And in those cases, I don't know if that would be an effective explanation. It might be very good at helping us predict things or representing something. But if we want the explanation, I think we have to figure out where else we're appealing to. It might not be in those contexts of the simulation that we're appealing to. It might be something like the theory, but then we need to shift the focus on what's providing that grounding, not the simulation, but that background theory instead.
Yeah, some of this feels a little bit reminiscent of when everyone was learning, when I was taking physics in undergrad, all the times like there'd be this you characterize something as physics versus math.
Yeah.
And sometimes a lot of the explanations was just like people just characterized as math and they wouldn't be satisfied with the explanation. But really what you had, in order to give you the result, they had to describe the algorithm that you had to do by hand in order to get the answer out. And it started to feel like this is like a similar thing when it comes to computer simulation.
Yeah.
It's just that the human is less involved.
Yeah, I mean, it's questions like that that drove me to philosophy and led me out of astronomy because I was like, I do not find that satisfactory. But yeah, I mean, I think that's some of the stuff that's going on here and really trying to attend to what role it's playing in the reasoning process. To me, anyway, is like fascinating. But if we want to be able to ground these claims, I think that's also what we need to but pay closer attention to and discuss more explicitly. Yeah, for sure.
Okay, we have some questions from the Zoom audience. So I don't know the order, but Peter, can you unmute yourself and ask your question?
Sure. One of the comments that you made was that prediction and explanation don't necessarily imply one another, or that they don't necessarily go together. There's a stronger claim that Nancy Cartwright made famous over the years by saying that they actually pulled in opposite directions. That is to say, precisely insofar as you pursued explanation, you impeded your ability to make predictions. If you were looking at some complicated gravitational system and insisted on explaining it with Newton's laws, you wouldn't get very far because you wouldn't encounter the kind of approximations and rules of thumb that are used to pursue this. And she does the other examples with the Lamb effect and many other instances and how the laws of physics lie. I wondered whether you think of what you're doing as a weakening of the Cartwright thesis, that is to say that they're not necessarily opposed, or whether they're just skew. Yours to say they may not have a necessary connection, and hers to say they pull in opposite directions.
Yeah. I think that's actually a really nice way to characterize, I think, what I'm trying to develop out. I think I'm interested in the fact that I think that there is something like a softened version of that exists, at least in sort of the ideal of what at least a lot of computer simulations are trying to do, because they want to do both that predictive and explanatory aspect. And again, at least from some of the discussions I've had with astrophysicists, that's often when you talk to them about what they think they're doing, that does seem to be like it. I mean, it's one of the ways in which I really appreciate what Cartwright's trying to point out, in that they often do pull in opposite tensions. And so I guess I'm interested in the cases where, I guess exploring where and how often that is true. But I do think there are some cases where when in the ideal, they go together. But I want to think some more about that.
Okay.
Thank you.
Yep.
Oh, is there more?
There are more, yeah.
Well, I defer to our Zoom audience.
Okay.
I'll come in later.
We have Tanvir Karim.
Hi, thank you for the wonderful talk. I'm a fifth-year grad student. I work primarily in observational cosmology, and I was very interested sort of like in your take on like simulation and like, being able to learn from things. Like one thing that, like one specific example that comes to my mind is, for example, when you do cosmological inference, one thing that we fundamentally have to use simulations for is getting the covariance matrix, because as you mentioned earlier, there is only one snapshot we can observe. So, and to get a covariance, you always have to like get multiple instances. So one thing that always made me feel a little bit uneasy, and I wanted to get your take on it, is the fact that your covariance matrix as good as many simulations you run and as accurate it can be. So, like if you do like the Planck inference of what cosmological parameters are, what H naught is, or whatever you want to do, ultimately that depends on like your covariance, because in some sense that is informing you. So the fact that we are learning like quote unquote like learning something about the universe by using simulation as because we are fundamentally limited by that, has always made me a little bit uneasy. And it's like, are we learning, or is this like some other thing that's happening in the process? I just wanted to, I guess, get like a philosopher's take on what you think about this whole thing. But thank you for the talk.
Yeah, I'm going to give a philosopher's answer, which is, yeah, I think that's a really good question to be asking ourselves. And at least for me, I think the answer is going to be in trying to like unpack and be really meticulous and thorough and speculative about what that reasoning actually looks like. I mean, I think, but it's also one of the challenges of the field is you only have those snapshots. So what else is there? And so I think that it also might involve sort of like considering what constraints there is on the kinds of claims. But one of the other things that I think is happening, at least within some of the history and philosophy of astronomy literature, is trying to look to other scientific disciplines to see how they assess or mediate these kinds of things. Are we deploying similar strategies to say like paleontology or history or geology, where they also only have these snapshots, though they're not like literal snapshots in the way that ours are, but they're also in some sense constrained to sort of going back and looking and just trying to triangulate within that space. So no, that's not a particularly good answer, but I think that that's the kind of question that if we pause and reflect on and try to unpack what that reasoning looks like, we're going to have a better sense of how justified we are in those kinds of claims.
Thank you.
We have Jamie on Zoom and then Chef, right? Okay, very good.
Hi, Melissa. Thanks for the talk. So my question, you talk about similarity as the sort of thing to be looking for in comparing simulations and observations. And you pointed to that, quote about, a lot of the work in establishing whether these two things are similar in the right way is going to come down to these assessment of the ways in which the kinds of similarity that's important for the given case. I mean, because obviously, if you just want to say two things are similar, you can always probably find some way that they're similar. And so it seems like a lot of the work is going to be done by, getting a bit more specific about the sort of appropriate kind of similarity that you're looking for in a given case. So I just wanted to invite you to maybe say a little bit more about your sense of, who gets to decide what these relevant similarity relations are, whether you think there's anything more general to say about the kinds of similarity that are going to be important in, say, astrophysical simulations, or whether this is going to end up being a very local enterprise.
Yeah, I mean, that's a really great question. I haven't thought a lot about it. I mean, my inclination is, I think that's partly why observations are particularly interesting, because there's not much else besides the observations. And also just in terms of like acquiring a specific amount of data, I think that's one of the things that can be really relevant. But I think it's also going to be a matter of just considering sort of where the field can still obtain more information and where it can't too. So again, I'm thinking if part of the similarity assessment is about, are we producing, blue stars? Are we producing these kinds of things? Those at least correspond to some extent with observations. Those are going to be, more useful. But I think there's other ones like accordance with sort of theory, maybe we're able to get just as similar of something from, using Newtonian dynamics or, even other sorts of like odd features. Again, Jamie might know this, but I also do think a lot about the tensions between lambda-cold dark matter and Mond models in particular in theory. And, there are some cases there where similarity ends up being favorable on some scales in favor of like Mond rotation curves and matching that kind of observation, whereas lambda-CDM doesn't do so well on small scales. And so I think those are some of the places where there really is like a harder tension in thinking through which similarities are appropriate. And there, I think it ends up being a matter of, considering community standards of what counts as evidence, but then also turning to what that evidence is actually trying to claim. So.
Thanks.
Yes, very interesting talk. I guess my question is in two parts. So one is that I like this distinction like Peter and others raised, that sometimes you want to come down on the side of prediction versus explanation. The more unknown the model is, the more I would imagine you want to come down on the side of prediction, right? You're trying to pin down the model more than explain. And the more you maybe understand things, then you want to explain. So for example, in the solar system, if you were to try to say something about how the planet's orbit or the asteroid belt and how it might have been a planet at some point, you think about different models there, and that's pretty well understood physics. But if you're looking at the plasma around a black hole, there is a huge raft of things we just don't understand about conduction and viscosity and things that govern that. So I just wanted to ask the general question, how do you make this, when you're entering into some field of study, it seems like it's very bespoke. I mean, if you're doing black holes, you would be going in one direction versus something else, you're going in a different direction. And then what I'm getting at is, how do you steer the next observations?
Yeah. Because
the whole point is, how do you do better?
Yeah.
Right. And so we'd like to be able to design the next set of instrumentation or to use panchromatic data, and I guess I'm just interested in how you formulate this a little bit more rigorously and philosophically. Like this is when you go for the prediction side.
Yeah. I mean, my natural inclination is to appeal to sort of just like old school philosophy of science and
I don't know what that
but
is.
I'm trying to think it out loud. So I mean, a lot of there, it's you look for the crucial experiments, you look for the crucial observations that would help you determine the difference between one model or another model. There's a feature in sort of our simulations that we accidentally discovered where some settings on our some settings in our simulations helped us produce what's called a spoke structure. I don't know if I have any here, but so this right here, a spoke structure, and some never produced a spoke structure, and so it turns out that's a feature that actually happens in some ring galaxies, and it allows us to say, okay, well, this kind of setting or this type of simulation predicted that the structure would be there and this other one didn't. And so there's a sense in which those are like the nice cases where you actually have something that comes out of them that's defining, that's different, that is predictively different, and can in some ways help push forward what we should actually be looking for, what we should be observing. It's those features, or trying to find those features that occur in one case, but don't occur in another case. But I think that that's really hard to come across in actuality. And so in those cases, I think it's a lot harder to figure out what to actually be doing the observing of. I mean, there's also the background worry anytime prediction is talked about is the fact that there are other cases in models and computer simulations that I think are problematic about relying too heavily on prediction, which is the fact that if MOND proponents are correct, their models and simulations predict rotation curves better than lambda CDM, you know, with higher accuracy, with higher similarity to the actual data. And I think that that's a really interesting case because at least amongst most astrophysicists I've talked to, they do not think MOND is anywhere in the right ballpark of being accurate, but nonetheless, they have these really predictively accurate models on small scales. So how do we rectify, you know, again, sort of best theory of not following MOND with the fact that those models are super predictive? I mean, I think that's where it comes back to purpose to some extent, and thinking about what the science is actually trying to push ultimately. Is it the fact that we want to be able to, say, predict rotation curves really, really well? You know, if my life was staked on the line, I would pick MOND over lambda cold dark matter for predicting those, but oh yeah. But I don't think if I wanted like which one's more likely to be correct, I would pick MOND. I would pick anything based in lambda CDM. And so I think predictive aspects are nice if you can come up with those differences, but then I think there's a sense in which you have to turn something back towards considering the explanatory aspects as well, and considering it within the larger context of what's known within that area of physics or science or whatever, because it's at those junctures that the explanation that you want to appeal to isn't that MOND is our best gravitational theory. It's just something about that model does a better job at predicting in that context. So again, that's not perhaps as helpful beyond, like, it's nice where there's those predictive differences, because I think those start to bring to the surface what might actually be going on behind it, or at least nice cases where you can say this is there and this isn't there, why not?
Okay, are there any more questions?
I do have one final thing, because all of this discussion, the thing that's missing is a pre-selected set of criteria, which everybody agrees on and said, if you can do all of this, your theory is good. It's not the way science seems to work, right? So even your simulations, you might start off doing your simulation saying, I want to explain exactly the diameter of this ring. I want to know where is that wiggle? Why is there an extra spiral arm here? Why are there 3 spokes and not 4? What's the thickness of spoke? There are lots of things that you might say, I want to do. When you run your simulation, it doesn't do exactly everything you want. But then, you step back and you say, yeah, it's okay. I got a few spokes and they're kind of straightish. Yeah. And yeah, so you just move the goalposts and say, this is adequate, or this is similar enough, right? So then, that's something everybody can do. You do a model, you try to explain something. It doesn't explain everything you wanted, but you say, yeah, this is good enough, I think I'm in the right ballpark. And you say, yeah, you claim victory. But that's not the end of the story, because then you have to convince the community. And at the end of the day, it's that community's judgment that decides whether or not you have succeeded or not, right? It would be so much better if God or somebody just told you, no, not good enough, go back, do some more. Instead, it is this community. And then, then all the personalities come in, everybody's intuition comes in, and, we have to kind of grope around and say, yeah, we think this, because I think this is what's happening with MOND, right? Mond keeps doing a good job within their limited sphere,
Yeah.
but the rest of the community says, no, that's not physics.
Yeah.
You know, that lambda CDM, that's real physics. It's using GR, it does this, etc., etc. So it becomes almost a popularity contest, or maybe some collective human intuition, which is exactly opposite to what scientists think we are doing.
Yeah.
But the more I listen to you, the more it seems to me that it's all very fuzzy. Am I getting this wrong? Or?
No, I mean, I think it is
I
fuzzy.
was just gonna agree that
Yeah.
it seems as though the issue is on what the scientists think they're doing.
Yeah.
It seems as though a failure to recognize the underlying sociology about how science plays out, as though there is some kind of view from nowhere of people being able to just, I don't know, find truth. And though it's like particle physics seems to get around the issue of that kind of, I guess they're more uncomfortable with that kind of sociological kind of uncertainty, where they put the hard mark for discovery, they put like 5 sigma, as though that's not kind of it's still arbitrary. Why not 3 or 7?
Yeah.
And so it's like from God effectively.
But
God said 5.
Yes, God said 5.
but I think that's right. But I think
It's like a
that's
grounding problem.
yeah, but that's also where it's really interesting. And this is the thing that I wish was more of the focus in some of the scientific papers, is sort of the background, reasoning process for these kinds of things. It's not necessarily every, potential, acknowledging the bounds on your science is partly good science, but acknowledging too many, then you start to bring question onto your own sort of findings. And so there's this really odd and interesting tension with respect to that. But I think it also is about refining and trying to understand what that more sophisticated reasoning process is for any type of scientific claim that often is a lot more complex than what's talked about in the papers. I mean, this is why I really like doing embedded philosophy of science, because again, doing some of these projects, I wouldn't have known the thing that we found out about the spokes if I hadn't been in the room the day me and another postdoc were like, we think our computer simulation isn't working because we still have this thing happening. And we went to our senior PI and was like, why don't you go back and look at the objects? And so we went back and looked, and we're like, sure enough, this is something that's actually there. But that's not necessarily the kind of thing that will make it into our paper, but nonetheless is one of the sort of like social contextual aspects that gave us confidence to continue pursuing it in this kind of thing. And so I think a lot of times, and this is one of the things I'm trying to think through as a philosopher, is like, what would that more advanced reason, or not advanced, but like complex reasoning process look like? And anytime you start to introduce more of those complexities, it makes it more couched or interpreted as couched or cautious, or not as grand as it might be, but nonetheless is part of what's actually going on in the reasoning process. And I think it's one of the things that's understood in some capacities within those smaller, scientific communities. And I mean, like the Mon stuff is what really got me into this. I was like, but based
what
on
more can they do? Right?
Yeah,
If they're able to explain everything.
but it was one of these things where I just wanted to have a better understanding of what that reasoning process within that community looked like, such that by some standards, like predictions, great, look, I got all the data points. I mean, but then I also think back to what my undergraduate astrophysicist supervisor told me as like a joke, but he was like, what's the difference between a physicist and an astronomer? A physicist needs 2 dots to make a line, an astronomer only needs 1. But really that joke has set off like that has been the focus of my dissertation and now my research program is if you laugh, but there's something in that, and I think it's so fascinating to unpack what's going on in that to understand.
A mathematician needs an infinite number of dots.
but those things I mean, this is also why sometimes I joke, in another life, I would have gone to an STS program and addressed this from that perspective.
No, it's really interesting. I only ask because some of these issues were brought up in, because I science technology studies, right?
Yeah.
I've looked into a lot of some of the literature there.
Yeah.
It resonates with a lot of the epistemology they were talking about.
Yeah. Oh yeah. It's one of those, like, if I could do another PhD, or if I was, I don't know what the right, like, not ableist word is, but like crazy enough to do another PhD, it would be the STS stuff. Because I think that really, there's something about that social aspects to what's being valued, that is in some ways underlying some of it to some extent. Why do we like prediction more than explanation, or explanation better than prediction? Some of us just find it more satisfactory.
Okay, yeah, let's thank Melissa again for a wonderful talk.
We kept you for an hour and a half.
Oh, that's delightful.
Yeah.